So yes, as I was saying, we will be talking about the Fabry-Perot interferometer. Right. Now here we have two parts, Fabry-Perot and interferometer, and this is just one of the types of interferometer. There are many other types as well, you know, right? Say Michelson interferometer, you know, Young's double slit experiment that was done, Newton's ring, and all that stuff. There are lots of interferometers. So basically, first we will talk about this interferometer. Now what is an interferometer? As you know, basically an interferometer it is a device which causes interference between two or more waves. Right. Now we will be here talking about electromagnetic waves. Right. Now you see, before I start with electromagnetic waves, you must remember that the Maxwell's equation for free space, we can actually manipulate it and write it down in two very concise vector expressions. Let me just write it down. So this is the expression for the electric field, right? And similarly, we can have analogous expression for the magnetic field. Now you must be thinking, why are we talking about the Maxwell's equation all of a sudden in this case of interference? Now the reason is that, let me now concentrate on this equation. You see, so basically what this tells us, it basically gives us an expression which describes the optical disturbance, and basically this is, as you can see, it's a second order homogeneous, right, partial differential equation. Right. Now what's so special about this second order homogeneous partial differential equation? The special thing is that this basically obeys superposition principle. Okay. Now, and that is the basic idea behind the interference. So what we can say is that the resultant electric field intensity at a point, right, a resultant electric field intensity at a point where two or more light waves overlap will be what? Will be basically equal to the vector sum of the individual constituent disturbances. So this will be basically vector sum of individual constituent disturbances, and this is what? This is due to this superposition principle, right? So basically you see, the optical interference corresponds to interaction of two or more light waves, and this yields a resultant irradiance which will deviate from the sum of the component radiances. That means if we have a total irradiance because of two components, then there will be some extra term, not just I1 plus I2, there will be some extra term, and this is basically due to this superposition principle. Okay, little bit more details. So let us, for the sake of simplicity, let us consider 2 point sources, S1 and S2, which are emitting basically monochromatic waves. of frequency in a homogeneous, same frequency, right? Since I am saying monochromatic, so same frequency in a homogeneous medium. Now let the separation A between these two sources, the separation is A, this let us assume is much greater than the wavelength frequency, right? Now what we will be interested in is the point of observation, and this will be very much far. So the point of observation, say P, it will be very far from the sources S1 and S2, right? So what will happen is that as a result, this far concept, what will happen is that the wavefronts at P will be basically planes, right? Now let us consider only linearly polarized waves, which has the form, say, E1 RT is equal to E01 cos of K1 dot R minus omega t plus epsilon. You know these terms basically. I am not going into the details since I will be mostly interested in the irradiance and the interference term. Okay, this will be cos K2 dot R minus omega t plus epsilon 2. Now you see the irradiance at point P, the point of observation. This is basically given by okay. Now what I am going to do, I am just going to concentrate on this term only, this E square average. So let me just write it down, this term. So basically we have E1 square plus E2 square and square along with this vector sum, right? E1 dot E2. Now you see we have to consider the average, and when we do the averages, then what we will have is basically average due to this, average due to this. So the total average will be this, sum plus this, no problem, and there will be this average due to this term. So let me just name this as, so if this is basically I, total I, and let me just name this I12, then I can write I12 as this. This is basically the interference term, and I can write the I12 as E01 dot E02 into cos of delta, where this delta is equal to, you see, K1 dot R minus K2 dot R plus epsilon minus epsilon 2, right? And this is basically, you see, known as phase difference. I know you know all of these things, but let me just revise this for the sake of completeness. Okay, so basically we are now talking about this interference term. Remember, this is a time average concept, just overall average concept, right? हाँ बोलो. You are right. I have shown you this thing, right? But now I am just talking about in terms of only. So basically you can say right now I am talking about just E square. Okay, I'm just talking about this. You are absolutely right, because this is the actual stuff which will be coming into play. Here we will have the changes involved. There will be no change regarding this constant, so that's why I'm just not taking them into account. Okay, ठीक है, good point. Acha. Now you see, as I was saying, so this is the phase difference, and this basically arises from the combined path length and also the initial phase difference, phase angle difference, which is this one, and this is the path length. Okay, so this is the two terms. So basically you can say that it is basically equal to the sum of these two terms. Fine. Now what next? Let's move forward. Now you see, the most common situation is when, so common situation is when we have this E01, this is parallel to E02. Okay, so what happens is that in this case we will have just the scalar relation, and so I can write it down as this E01, E02, right? So we will do the scalar treatment, which is much easier to understand. And now as a result I can write down by 2, and then similarly the same for I2, I am not writing it down, and for I12 basically we will have I can write it instead of E1 and E2, and now I am using just I1 and I2 and then cos delta. Okay, so as a result my total irradiance I can write it as I is equal to I1 plus I2 plus twice of I1 into I2 into cos of delta. Right, now as you can say, the maximum irradiance, as you can see here, when will it happen? This happens when, of course, cos delta is equal to 1, right? And this happens when delta is equal to 0, plus minus 2 pi, plus minus 4 pi, and so on. And here in this case, for this maximum irradiance case, we have I max equal to I1 plus I2 plus twice of I1 into I2, right? And this is basically your total constructive interference. So basically you see, we are having a redistribution of energy and all that. Sometimes there will be maximum, sometimes there will be minimum as well. So similarly we can have, you see, so this is the case for maximum irradiance, right? Now for this case, when cos delta is between 0 and 1, what happens? The waves are out of phase, right? And here also we have I1 plus I2 is less than I max in this case, and also in this case we can say that we have constructive interference. Now what happens at delta is equal to pi by 2? Here you see cos delta is equal to 0, and so the optical disturbances are 90 degree out of phase, and I will just write, sorry, I will just write I is equal to I1 plus I2. So there is no extra term. here. Now for the other case, which is basically 0 cos delta greater than -1. What happens in this case? In this case, basically we have destructive interference, right? Because now what we will have is this. And you see, the minimum irradiance results when the waves are 180 degree out of phase. That means when cos delta is equal to -1. And I will write it down as this. I minimum is equal to I1 plus I2 minus twice of I1 and I2. So basically destructive interference. And so when does this happen? Of course, this happens when delta is equal to plus minus pi. You see, odd multiples. Plus minus 3 pi, plus minus 5 pi, and so on. So this is the total destructive interference. Right. Now you must be thinking, okay, so what next? Now what next is that when is this constructive and destructive interference most dramatic? When I am saying most dramatic, it means if I observe this, then when will it be most dramatic? During observing, it will be most dramatic when, for the case of constructive interference, I will just see a very bright, something very bright. And in the case of destructive interference, I will not see anything. That means total darkness. Right? So when will that happen? And the answer is this. You see, so this is yet again a very special case. So the most dramatic case will be when, you see, when the amplitudes of the both waves are equal to each other. That means E01 is equal to E02. Right. So you see, in this case, I1 will be equal to I2 equal to I0. And so the total intensity, I can write it down like this. Now this is the case for constructive interference. Twice of I0 into 1 plus cos of delta, or this is basically 4I0 cos square delta by 2. Okay, and you see, we can get this relation from here, which is I min equal to 0 and I max equal to 4 of I0. So this is the most dramatic case. That means when, for the case of maximum, we will have something. So this is like digital case, you see. So it is like a digital case. So one is 0, one is 1. So either we don't see anything or we are observing a lot of things. Something like this. Any questions till now? Now देखो digital कैसे की हो? Input digital we can have only two possibilities, either 0 and 1. Here you see, I am just saying, basically dramatizing. In this case, the minimum is you will not see anything, total darkness. And this case, you will have total brightness. 4 times extreme redistribution of energy. This is what I want to say. So what happens? Is this entirely actually 0 in this particular point? No, the energy has been redistributed to this point. So extreme redistribution of energy. Till now I have talked about very basic ideas regarding your, what you can say, basic ideas regarding interference, right? Now, before I talk about the next topic, which is the interference fringes, and then I will talk about Fabry-Perot interferometer, let me again talk about the very important point of the conditions for interference. You might have guessed this from what I have said till now. Now, you see, one of the most important condition to be met if two beams are to interfere and produce a stable pattern. And what is that condition? I have been repeatedly, you will remember, telling you that we are considering two beams of the same frequency. So the most important condition is that they need not have the same frequency. But the important condition is that they must have very nearly the same frequency. This is important. And why? You see, if there is a significant frequency difference, then what will happen? This would then result in a rapidly varying, time-dependent phase difference. And remember, we are taking an average. So what will happen is that this will cause the I12. So if there is significant frequency difference, then what will happen is that the average of I12, that basically I12, which is an average quantity, this will just average out to 0, right, during your detection interval. And so what's the overall effect of having this interference? Nothing, because interference means we want to do something so that this thing must exist. So we should not do, we must remember not to change the frequency of the two sources by a lot. Now suppose if both the sources emit white light, then what? Now you see, in white light we have different components with jar. So the red component will interfere with the red component, the yellow will interfere with the yellow component, and so on and so forth. And as a result, what we will observe is many similar, slightly displaced, however, remember, overlapping monochromatic pattern will be produced. And this will cause a total, what we will see is that you will see a total white light pattern. However, remember that it will not be as sharp as a quasi-monochromatic pattern, but it is important to remember that white light will produce observable interference. Now, the clearest pattern which exists when the interference waves have equal or nearly equal amplitudes. So first is they must have the nearly equal frequency. Now I am saying is that the clearest pattern. Now what we want to do here, we are talking about an MSc practical, right? Of course I am not going to talk about an experiment which is very hard to understand or which is very hard to, where the fringes are very hard to observe. But we will talk about something where things must be very clearly observed, right? So this is what I am talking about. The clearest pattern exists when the interfering waves have equal or nearly equal amplitudes. Right. So what will happen is that the central regions of dark and light fringes will then correspond to complete destructive and complete constructive interference. And as a result, as I was just saying, the digital output. So we will have a maximum contrast. So basically maximum contrast. And what does this mean? Maximum contrast means 0 and 4i0. So basically 0 and 4i0. This is, you see, the maximum contrast. Okay, now last very important point, but not the least, again, is that you see, for a fringe pattern to be observed, the two sources, they need not be in phase with each other. Sometimes a somewhat shifted but otherwise identical interference pattern will occur if there is some initial phase difference between the sources. That means epsilon minus epsilon 1 minus epsilon 2 is finite. But as long as it remains constant. So, such sources, what are they called? They are known as coherent sources. So, the phase difference should be fixed. Okay. Although the initial phase difference may be finite. Understand? Coherent sources. So, fine. So, you see, till now I have talked about the very basic ideas regarding interference, this I12 term, basic mathematics regarding that. Then I have talked about the condition for interference. Now, let me spend some more time on the interference fringes. Right. Now you must remember that I have talked about the equal amplitude case. Equal amplitude case. And there we found this expression for intensity. I is equal to twice of I0, 1 plus cos of delta. Right. And this is what? This is equal to 4 of I0 into cos square delta by 2. Fine. Now, it is important to remember that this expression will be applicable when the separation between, so this is applicable when separation between the two sources, remember S1 and S2, it is small in comparison with R1 and R2, right? And also, and you see, when the interference region is small, this is important. Now, under these circumstances, what we can consider, we will consider under these circumstances E01 and E02 to be independent of position. That means they are constant over the region examined. Now what? As a result, what do we get? So, if the emitting sources are of equal strength, then we already know E01 equal to E02, and so I1 equal to I2 equal to I0. And as a result, now I am going to write down the entire expression. So delta, I am going to write it in the complete form. So 4 of I0 cos square half of K R1 minus R2 plus epsilon 1 minus epsilon 2. Right? Now, as we know, the irradiance maximum, where does it occur? It occurs when delta is equal to twice pi m, provided that m is equal to 0, plus minus 1, plus minus 2, and so on and so forth. Similarly, irradiance minimum, this is maximum, this is minimum. Minimum, where does it happen? This happens for this values, m prime. Similarly, the value of m prime will be plus minus 1, plus minus 3, plus minus 5, and so on and so forth. And you see, we can write, in fact we can write like this, m prime is equal to twice m plus 1. See, this matches. Now let me rewrite these two expressions using this the values of m that I have shown you. It is possible to rewrite the maximum, right? So maximum irradiance, we can write R1 minus R2 is equal to 2 pi m plus epsilon 2 minus epsilon 1 divided by k. And similarly, minimum condition, I can write it as R1 minus R2 is equal to pi m prime plus epsilon 2 minus epsilon 1 divided by k. Right? Now you see, any of these equations, both of them basically, they define a family of what? Surfaces, each of which is basically a hyperboloid of revolution, where the focus is located. Focus is at S1 and S2. Now, you see, if the waves are in phase at emitter, then what will happen? Epsilon 1 minus epsilon 2 is equal to 0. And so, this above expressions, it will be simplified to this form. R1 minus R2 is equal to twice pi m by k, and this I can just write it down like this, m lambda. Similarly, so this is the max condition. And what about the minimum condition? I can write it again, R1 minus R2 is equal to pi m prime divided by k, right? And this is basically equal to half of m prime into lambda, right? Now you see what will happen as a result of this. We will see dark and light zones in the region of interference. So we will observe dark and light zones in region of interference, and this is basically known as your interference fringe. Okay, now this is the three main ideas. So basically we have talked about basics of interference, condition for interference, and interference fringes. The two waves must also have the same polarization state. This is also important for observing the interference pattern. That means their electric field vectors must point in the same direction. Here. So let me write it down. So their electric field vectors must point in same direction. Okay. So if there are no more questions, just let me do a basic discussion sort of. So basically what we have discussed till now is interference, which is a phenomena where what? Where two waves superimpose and form a resultant wave of greater or lower amplitude, basically redistribution of energy, and this redistribution of energy is basically the fringe pattern. Okay, so basically a hyperboloid of surfaces. So basically this is your fringe pattern. Fringe pattern. And what is the fringe pattern? Fringe pattern is basically showing us the redistribution of energy. Okay. Now similar to interference, we do have diffraction, another phenomena. And what happens there? So basically, diffraction refers to various phenomena that occurs when a wave encounters an obstacle. Now in classical physics, this phenomena is described as the apparent bending of waves around small obstacles and the spreading out of waves past small openings. So remember this. You might be asked in the Viva also. So what's the basic difference between interference and diffraction and all that stuff? Okay. And so after talking these details, next we will talk about interferometer, which is basically instrument which work by merging two or more sources of waves. Basically here we are talking about light. And as a result, the instrument will create an interference pattern. Now, it is not just important to create the interference pattern, but the instrument must produce interference pattern which can be measured and analyzed. And as a result of analysis, it should tell us the information about the source itself. Okay. Now, as you know, there are two types of interference, division of wavefront and division of amplitude. Now I am not going into the stuff, but basically now, since there are no more questions, so I will now enter the topic of Fabry-Perot interferometer. Okay. Suppose I ask you, what do you mean by fringe? Ki bolbe bolo to? Suppose I am asking you. I am just talked about the fringe pattern. And I told you that it shows us the redistribution of energy. But if I ask you, what is a fringe? Then what will you say? Basically, what is a fringe? Fringe is basically a locus of constant phase. Okay, this you must remember. What is happening? Maximum irradiance, this condition. So what will happen in the case of maximum irradiance? We will see something very bright, right? What if we have equal amplitude? Then in the case of minimum irradiance, we will not see anything, zero. So what's the locus? The locus will be a dark region, right? The fringe pattern, in the entire fringe pattern, I will see something which is very dark, corresponding to the minimum irradiance scenario. And for the maximum, I will see something bright. And this corresponding patterns of dark and bright, this is basically the interference pattern. You see? Yes. What you are seeing here, basically, this is the fringe pattern observed during the experiment in our lab from the Fabry-Perot interference setup. Okay. So you see there is a dark region and then there is a bright region. Now this is not entirely dark and this is not entirely bright, but there is partial light in between, but still this is somewhat dark, then somewhat bright, then somewhat dark, then somewhat bright. So this is basically a dark and bright pattern. বুঝতে পারছো? Interference fringe system. So fringe constant locus of constant phase. Now here the phase corresponds to minimum, here the phase corresponds to maximum, something like this.